Swayam Prabha. Digital India. Educated India.
Hello students. In today's lecture, we are going to continue our discussion on entropy, and with the definition of entropy introduced to you, and I have already discussed how to determine entropy in different processes. Now we are going to focus on the concept of entropy to predict the direction of spontaneous change and the condition under which the system attains a new equilibrium. Now let me remind you that the second law of thermodynamics gives us the definition of entropy as ds is equal to dq reversible by T. And therefore, if I integrate this exact differential ds, I have information regarding the change in entropy as the system goes from an initial state A to state B. Now we have already seen delta S can be measured for both reversible and irreversible processes. While it's very important to know that I need to understand what the initial and the final state is for an irreversible process, and then fabricate a reversible process to connect those two states to be able to evaluate delta S for that irreversible process. And the absolute value of S, if you want to estimate its value, then you would have to take help of the third law of thermodynamics. Now, I've also showed you that S does reflect the degree of disorder in a system, and that we connected to the absolute value and the change in entropy that we see when a system passes from a very low temperature to a very high temperature, whereby it can undergo heating as well as phase transition at certain temperatures. Now, if I combine the first and the second law of thermodynamics, then this is the mathematical statement of the first law of thermodynamics, which says du is equal to dq plus dw. Now, the second law says TdS is always greater than or equal to dq. I will actually show you how to write this down in terms of the Clausius inequality. In today's lecture, that would be what we are trying to obtain, the mathematical statement of the second law of thermodynamics. Let me mention that the equality sign holds when the system is at equilibrium. So, in this case, if I combine the first and the second law, in general, I can write TdS must be greater than or equal to du minus dw. And the equality sign holds when the system, I'm looking at reversible processes, which means that the system is in equilibrium with its surroundings. Now, if I have dw equal to minus pdv, then I can very easily write that this dw I am going to replace by minus pdv. So, I have TdS is equal to du plus pdv, and correspondingly I can write down du is equal to minus TdS is equal to plus TdS minus pdv when the system passes from an initial equilibrium state to a final equilibrium state through an infinitesimal process involving change in entropy ds and change in volume dv, and correspondingly the associated change in u is du. Now, as you see, this combination depends on very crucially on identifying this mathematical statement of second law of thermodynamics. And when I combine these two laws, I find an expression which is known as the thermodynamic, which is very important in thermodynamics for practical applications in real systems. Therefore, the task we have at hand is first, how do I arrive at a relationship like this? And once I establish this, then I need to understand how I'm going to use relationships like this into practical applications. So let me now go ahead and talk about what is known as Clausius inequality. Now, for any reversible engine operating in cycle between two temperatures Th and Tc, where Th is greater than Tc, I know that the efficiency of the reversible engine is given by 1 minus Tc by Th. And therefore, if I integrate over the entire cycle for this quantity dq by t, I must be having this equal to 0 simply because this is equal to delta S, and since I have a cycle and S is a state function, therefore the value of this integral must be equal to 0. Now, if I consider any arbitrary engine which is not reversible, that is, which is irreversible, which is operating in a cycle between the same two temperature reservoirs maintained at the higher temperature Th and lower temperature Tc, but with the same input of heat QH from the hot reservoir, I can write this that eta is going to be less than eta reversible. Why is that so? Please remember, eta is by definition the amount of work done by the input heat as written here. So, eta in this case would be in general equal to modulus of W divided by QH. In this particular engine, this is W. If it is irreversible, then I am considering eta is equal to W irreversible magnitude divided by QH. Since W irreversible is always less than W reversible, therefore, I can write that eta for this irreversible engine must be equal less than eta reversible. For any cyclic engine, I know that eta is equal to 1 plus Qc by QH, which we have already seen. Therefore, I am now going to rewrite this expression by writing out the expressions of eta that I have got here and here. So, I find that eta, that is 1 plus Qc by QH, I put it on the left hand side in place of this eta, and this would be less than eta reversible. So, I put back this expression on the right hand side and then I rearrange. When I rearrange, I find that this means that QH by TH plus QC by TC must be less than 0. Now, as you understand here, I am talking about a heat engine which during each cyclic operation, it has two instances of absorption of heat when kept in contact with a reservoir, and here there are two instances of doing so when I have the system in contact with a hot reservoir at temperature Th and a cold reservoir at temperature Tc. Therefore, I can write this expression in general as dq by t cyclic integral. So, it says that basically you are evaluating all the integrals that and adding them up over the entire cycle that you have seen here. And if the engine is irreversible, in that case, I will have this integral less than 0. What happens if this arbitrary engine is reversible? So in that case, obviously, once again, I will have cyclic integral of dq by t equal to 0. Therefore, for any given engine, irrespective of whether it is reversible or not, I can write that I will have dq by t less than or equal to 0. So when does the equality sign hold? The equality sign holds when I have a reversible engine, and the inequality sign holds where I have an irreversible engine. Now moving ahead, let me take this example where the system starts from an initial equilibrium state 1, goes to the final another state 2 by following an irreversible path. And then the system is brought back from state 2 to state 1 following a reversible path. So all of you would agree that this is a cyclic process. But what kind of cycle is this? The heat engine which follows this kind of transformation, shall I label it as a reversible engine or irreversible engine? Of course, this is going to be an irreversible engine. Now, I know that for any irreversible cycle, cyclic integral of dq by t is less than 0. So, in this case, this particular relationship must be valid, and then I can write down that integral 1 to 2 dq irreversible by t, that is this quantity when I followed the first irreversible step, plus 2 to 1 dq reversible by t. These are the two instances of that I can think of during the entire cycle, and the summation of both must be less than 0. If that is so, now the next thing to understand is that what is dq reversible by t? By definition, this is nothing but ds. If that is so, then I can write down this expression as I retain this integral as it is, but I replace this quantity by ds. So now I have this minus this integral is less than 0. But can I carry out this integral? The answer is yes. So if I carry out that integral, then I can write 1 to 2 dq irreversible by t minus S2 plus S1 must be less than 0, because here I have gone from, what I have done is, here I had a plus sign and now I have switched the sign of my initial and the final state, and therefore this plus sign has become minus, and all I am doing is I have just written down delta S for this integration, and here is the relationship. So if I take it on the other side, what I find is S2 minus S1 must be greater than 1 to 2 dq irreversible by t. So this is exactly what I have written down in this final algebraic expression. So what is it that we have learned from this particular cycle? This particular cycle has one irreversible step and I have another reversible step. I know that if I know the two terminal states and if I have a reversible path connecting them, and dq reversible is the amount of heat exchanged at temperature T when the system passed from the initial state to the final state, I can define the change in entropy. But can I do it for the first irreversible step? Of course, here I am not interested in that. All I have done is I have looked at the reversible step and said, from here I can identify what the change in entropy is, which means I know what S2 minus S1 is. And I find that S2 minus S1 is greater than this integral. Now, what is the consequence of this? The consequence of this relationship is that I can say for a differential change in state, ds would be greater than dq irreversible by t. So, the mathematical statement of the second law of thermodynamics then turns out to be ds is greater than or equal to dq by t. So, the greater than sign that applies when the system is undergoing an irreversible process, and the equality sign holds for a reversible process. Now think about it. When a system is undergoing an irreversible process, it is a spontaneous change in state. So for a spontaneous change in state, what is the condition that the second law of thermodynamics tells us? It tells us the associated change in entropy must be greater than dq by t. Now, when the system is undergoing a reversible process where it is at equilibrium at every stage, then ds would be equal to dq by t. Now, if it so happens that there is a process which is trying to take the system from an initial state to a final state with which there is an infinitesimal change in entropy involved, which is less than dq by t, this process is not going to be spontaneous. And therefore, we would say that the process in this case associated with the change in state is not permitted, or it is non-spontaneous. Therefore, this has to be the relationship exactly opposite to this. Therefore, the mathematical statement of the second law of thermodynamics then gives us an outline of the condition of spontaneity and equilibrium in terms of the change in entropy. Now, if I apply these concepts to the transformations in real systems, then I find that from Clausius inequality, ds must be greater than dq irreversible by t by the Clausius inequality. Now, if I have an isolated system, in that case, during an irreversible process, what would be the simplification? There will be dq irreversible equal to 0. This would also mean that ds is greater than 0. Therefore, we conclude that for a real transformation in an isolated system, upon withdrawal of an internal constraint, the system spontaneously changes towards that direction that increases the entropy. So, this is a very important statement. So, what kind of system that I have? I should have an isolated system. This isolated system should be made to undergo a spontaneous change in state. So, that is going to be your experiment. And your observation would be that the system would spontaneously change towards that direction that is associated with the increase in entropy. So, let me take an example and summarize this, what I meant by this statement, but let me give you further elaboration on this statement by saying that any natural change within an isolated system is accompanied by an increase in entropy, and this entropy would then continue to increase as long as the changes occur within the system. When the entropy attains its maximum value, then we would say that the system has reached a new equilibrium state. So, if I am inducing a change in state and following the change in entropy of the system as it passes from an initial equilibrium state to its final equilibrium state, then we will see that it spontaneously changes in this direction, and it continues to do so till the entropy attains a maximum value. And this is where I will say that the new equilibrium state has been reached, and therefore from this time onwards, irrespective of when you measure the entropy, if it is possible to evaluate the entropy of the system, you will find that the value is going to be independent of time. And under such condition, as you see, this is the direction of spontaneous irreversible change in state because it is associated with an increase in entropy. Now, if I want to go from here to this direction, that is associated with a decrease in entropy. So, this is not the direction of spontaneous change. And when the system has attained the maximum value of entropy, there is no further change required, and the condition of the new equilibrium is that if you want to reversibly and infinitesimally want to change the state of the system, it will not undergo any further change, and therefore ds would be equal to 0. So let me wrap up this discussion by saying that if I have an initial equilibrium state of the ideal gas as taken from this example, where the ideal gas occupies a smaller subcompartment in this insulated box, and the rest of the box is evacuated, and if it is separated from the evacuated portion by an adiabatic separator, I can induce a change in state in this isolated system by adiabatically withdrawing the separator over here. Then the question that we ask is, will the gas undergo isothermal reversible compression, or will it undergo isothermal irreversible expansion? Now here, let me once again ask you the question, what is the change in entropy of the system as it goes from TVIN to TVFN? We have seen that delta S for 1 mole of the ideal gas here will be R ln V final by V initial. Now, I understand that delta S from this expression, it would be greater than 0 if and only if Vf is greater than V initial. And therefore, what would be the direction of spontaneous change in state of the gas here? It will try to make the final volume greater than the initial volume. Therefore, the ideal gas will spontaneously expand under the given experimental condition, and therefore I would say that the final state will not at all be the compressed ones that I have shown here, but it can be any of the expanded states. Next comes the question, obviously, is when the gas starts to expand, where will it stop? Would it stop here, or would it stop here, or would it go all the way and fill up the entire box? Here, I understand that delta S, if it goes on increasing, here the final volume is larger than the initial volume. In all these cases, delta S is greater than 0. But when is the new equilibrium state reached? Under the given condition, when the entropy value reaches a maximum. So in this case, I have to look for the situation where delta S becomes a maximum. Now delta S, what is that value here? That is S final minus S initial. In all these three cases, I am starting from the same initial. And therefore, SF will be a maximum only when delta S is a maximum. And if delta S is maximum, in that case, I will say that my final equilibrium state has a maximum entropy. Now look at the expression of delta S. So delta S will be a maximum when Vf is a maximum. Therefore, when the gas expands and fills up the entire box, that is the condition when, under the given experimental setup, we can achieve a maximum entropy of the given setup, and therefore the ideal gas will spontaneously expand till it fills up the entire available volume. So now that we understood this, please remember that the condition of spontaneity and equilibrium we have discussed for an isolated system in terms of entropy. Little boy Calvin was doing a history homework, and this is something that he came up with when he was doing his history homework. He says, history is the fiction we invent to persuade ourselves that events are knowable and that life has order and direction. With apologies to the creator of Calvin, I find that you can very easily modify his statement and use it to describe the purpose of introducing entropy in thermodynamics. It says that for an isolated system, entropy is the state function we invent to persuade ourselves that events are knowable and that life has direction. At this note, I will conclude this lecture. Thank you.